Welcome back. So far, we covered consensus dynamics and synchronization dynamics in the last two videos. And for scientific and Department of Defense applications, I already mentioned that the synchronization dynamics are more important, meaning that when you have not only followers but leaders in the network, you can shape the behavior of the entire swarm by injecting commands to the leaders or the root nodes. From this perspective, it is applications to ground aerial space or water underwater vehicles of synchronization dynamics or leader follower networks are more important as compared to consensus type of dynamics where you don't have any leaders or leaderless networks. So because of the importance of leader-follower networks, we started to investigate synchronization dynamics in the past lecture, but we focused on single integrator dynamics. It is important to note that single integrator or scalar systems are nice, but double integrator dynamics are more common. Especially, you will see in some parts of my lecture series on my channel, in different lectures, I have complicated nonlinear systems where after I make a state transformation, or sometimes feedback linearization, I can write systems of nonlinear dynamics into some double integrator dynamics. And the one example I have on my channel is this non-holonomic system. Not particularly on this playlist of multi-agent systems. If you're interested, leave a comment and I will let you know. Anyway, for at the vehicle domain, when you deal with, for example, quadcopters, you can think each quadcopter or aerial vehicle, fixed-wing airplane, each mode like the pitch, dynamics, roll dynamics, and dynamics and yaw dynamics. You can think they as the independent double integrator dynamics that are decoupled from each other. Of course, if you are performing a complex maneuver, they are not decoupled, but if you are carrying loads, driving passengers from here and there, mainly you can approximate your roll and pitch dynamics as the double integrator dynamics. Likewise, your altitude problem, your height, you can adjust your vehicle's height based on double integrator dynamics. So double integrator dynamics is one of the most important high-order dynamics when we deal with multi-agent systems. And today we're gonna generalize what we learned on synchronization dynamics or leader-follower networks to we generalize them from single integrator to double integrator dynamics. So we have xi that equals to vi. You can think xi is the position, vi as the velocity, vi dot as the acceleration. So ui control action is basically affecting your velocity change or acceleration, and your velocity change drives your system. And as our control signal, I am going to use, I put a gain here, alpha, and beta here. This is not new. We use this control signal when we deal with xi that equals to ui, the single integrator dynamics. But, this protocol, basically the aim of this protocol is to synchronize each agent with respect to a given command, available only to leader agents. For leader agents, particularly, they are the ones, root ones for the case of directed graphs. Ki is 1, otherwise 0. And we have this new player here. Basically, it is to, since we have double integrated dynamics, once position xi converges to this command for each agent, then we should feed velocity back as a feedback term to stop those vehicles at their particular locations. So it is like the position and the velocity command to your system. So with this goal in mind, when we deal with the synchronization problem for leader-follower double integrator agents, we form this error dynamics xi minus c. We compute ei dot, which is xi dot minus c dot. Command is 0. Maybe later we can discuss. We discussed for the actual synchronization problem what happens when the command is time varying. I'm not going to discuss, I don't want to repeat the same material, but you can extend the stuff that we are discussing for the case when we have time varying commands. All right, so EI dot becomes XI dot. This is 0, which is VI, because XI dot is VI. And VI dot equals UI. UI is, now I am writing everything in terms of the error. That's why I am subtracting and adding the C, such that it is, basically I am adding 0, but this minus C and C, this becomes EI. This becomes minus EJ. This becomes AI for leaders. For followers, KI is 0. Or in compact form, basically, you have from the first dynamics, E dot becomes V. V is V1 to Vn. E is E1 to En. These are now vectors, no longer scalars. And V dot becomes minus alpha multiplied by L and K. L plus K is F. If you remember from the previous lecture, I am using the same convention, F minus beta multiplied by V. So in compact form, this is our closed loop system. You can represent it like E dot V dot compactly like this. And alpha and beta are positive scalars. Basically, aim is, if you choose alpha beta such that this matrix becomes Hurwitz, then error goes to 0 and velocity goes to 0. You can use different tools to analyze this system. For undirected graphs, F becomes F transpose. In directed graph subject to the same subject spanning tree, F doesn't necessarily symmetric, so F doesn't equal to F transpose, but either case, for undirected connected graphs or directed connected graph subject to spanning tree, F has eigenvalues on the open right half plane, or minus F or minus alpha F has eigenvalues on the open left half plane. So this is Hurwitz, but you need to play with alpha and beta to make sure the entire system matrix is Hurwitz. I will show a spatial case when we have undirected graphs. Something nice pops up as compared to directed graphs. But first, let's simulate this. This example. I am using the same directed graph from the last two lectures. You can find the Laplacian matrix of this system, then you can obtain F as L plus K. What is L plus K? Again, I discussed in the previous video. It's called synchronization dynamics. So if you are watching this before watching that video, I will watch synchronization dynamics first, then the double integrator dynamics. Anyway, so I have some initial conditions for this, position states of the agents and velocities are 0. Simulation time is 50 seconds. I choose command to be 10, alpha and beta like this. This is basically ODE running the same stuff, same algorithm. X1 dot equals to, this is the 4 agents position states, the position dot equals to velocity 1, 2, 3, 4. It goes like this, so I use this convention. This is the entire ODE that I am simulating. First agent is the leader, that's why it has access to command, and these are the figures. I am simulating it with this ODE 45. So as expected, the position states of each agent converges to 10, and velocities become 0. So once agents approach their position commands, then velocity becomes 0. So, okay, punchline, even if you have undirected or directed graphs, as long as you make this matrix Hurwitz, then you are good to go. So I have some good news for the case of undirected and connected graphs when F becomes F transpose. So you can choose this Lyapunov function candidate alpha over 2E transpose FE. You can use F here. F is positive definite and symmetric. All right. For undirected graph, it is not necessarily symmetric for directed graphs. So we may or may not use this for directed graphs subject to spanning tree. So this analysis only for undirected connected graphs. Um, so I have this Lyapunov function composed of two terms. They are regularly unbounded. When error v0, this is 0, and this positive definite. So this is a proper Lyapunov function. I take the derivative v dot. I obtain alpha E transpose Fe dot plus V transpose V dot. I have alpha here multiplied by, I'm injecting E dynamics. I'm injecting E dot V dot dynamics here inside the brackets. This is the first term. This is the second term, and this is the third term. Now, if you look at the first term, this is a scalar, right? E transpose FE, FV is a scalar, like 5, like 10. It's a transpose of a scalar, one by one vector is itself. So I'm taking its transpose. So if I start from here, V transpose, F transpose, and E transpose E. F transpose, in F transpose, this transpose disappears because F is symmetric. That's why this analysis holds undirected and connected graphs. Instead of F transpose, I can write F here like in here. And if I do so, these two terms will cancel out with each other. I only have minus B, V transpose V. I started my journey, my travel with two friends, depending on error and V. At the end, I only have one friend. A term like minus e to the power of 2 or minus E transpose E in this case is missing, so I can only claim Lyapunov stability. Once again, if you're struggling about Lyapunov stability, go to my advanced control systems playlist and watch the video stability, Lyapunov stability, and more to get all the important tricks that we use in research in our daily control systems lives. Now, when you have a case like this, just Lyapunov stability, it is important to use Barbalat or a more powerful result like Lassalle's invariance principle. Here, I'm going to invoke Lassalle's invariance principle. I am looking at where the energy stops. Energy stops when V is 0. When V is 0, V dot is 0. I am now going through the dynamics here. V dot equals to minus alpha Fe minus BV. When I'm looking at what happens when V is 0, V dot is 0, the only remaining term minus alpha Fe is 0. Now, if alpha Fe is 0, then F multiplied by E is 0. And since F is non-singular, then you can multiply both sides by F inverse. So Fe equals to 0, both sides multiplied by F inverse, E equals to 0, since F is non-singular. So by Lassalle's invariance principle, you can show both error and V goes to 0 for undirected and connected graphs for any values of alpha and beta. In other words, I mentioned in the previous slide before the simulation, this one, for directed case or undirected case, as long as you make this matrix Hurwitz by properly choosing alpha and beta, then you are good to go. What this analysis that I just did shows you there, if your alpha needs to be positive, and for the sake of this result, beta needs to be positive, for any alpha and beta, this matrix must become Hurwitz for agents over undirected and connected graphs because this analysis holds for any positive value of alpha and beta. So, in other words, I mentioned that you need to check whether this matrix is Hurwitz or not. If you are, this is very important, if you are dealing with undirected and connected graphs, just use any positive alpha and beta and tweak it to improve performance, because any alpha and beta will make this matrix Hurwitz for agents over undirected connected graphs. This is not the case for directed graphs. Even if you have a spanning tree, you can take the same example. Either one of those cases in the same example, I did this yesterday, so I rely on my brain, but I think either one of these situations, I created an unstable agent trajectory since this graph is directed subject to spanning tree. First one is the root node. From root node, you can access directly or indirectly everywhere. So this is a proper directed graph subject to spanning tree. But if you use either alpha, choose it to be 10 or 15 beta 1, or alpha to be 1, beta to be 1 or 15, or 10 or 15, either one of these two cases, you can see system becomes unstable, meaning that this matrix doesn't become Hurwitz for any value of positive alpha and beta when you deal with directed connected graphs. So once you are dealing with directed connected graphs subject to spanning tree, make sure first choose alpha and beta. Before any simulation, make sure it is Hurwitz. Then your simulation will work. But as I just mentioned, if you are dealing with undirected and connected graphs, thanks to this analysis, You don't need to check if anything is Hurwitz or not. It will be Hurwitz. Just pick your alpha and beta to be positive and tweak it to improve the performance. I think you got my story. And this is now what happens in addition to this important analysis, undirected versus directed, with the flexibility on the undirected case. I would like to cover the formation. So for formation control, I will say first what I should say last. Eventually, for undirected case, any alpha beta positive will work for the formation case. For the directed case subject to spanning tree, you need to make sure this matrix is Hurwitz. Then your formation protocol will also hold. So what is your formation protocol? We are going to use the same formation protocols, the same principles that we did over the last two lectures. So wherever I see x, I'm going to replace it with x minus c. So here, initially, this was x. I am going to insert xi minus ci. Instead of xj, I am inserting xj minus kcj. And here, instead of xi, I'm using xi minus kci. And these kci's, as we discussed before in the previous videos, determine the shape of the formation. So to analyze, I am using this EI type of dynamics that also includes the constant bias that comes from these formations. When I take its derivative, these two guys will be zero. EI dot becomes XI dot, which is VI. And VI dot becomes the control signal formation protocol for double integrator dynamics with beta velocity term. So this error dynamics, once you add and subtract command, you can still write it like EI minus EJ. So you have the same compact form for the formation case, since we defined error slightly different, but at the end, your system matrix, your closed loop remains the same with the new error. So once you do so, once again, n alpha beta positive works for undirected connected graphs. For directed, you need to make sure this is Hurwitz so that your formation protocol works. I already explained you how you design this KC1, KC2 for the formation case over the last videos. If you haven't watched, please watch. You can directly watch the previous video, synchronization dynamics, or one before that, consensus dynamics. You can watch those videos until in the last slides of those videos, I covered the same formation case. Here we have I am using the same directed graphs. So I pick my alpha and beta. Since I'm using a directed graph subject to spanning tree, I go back and check if this is Hurwitz. With this alpha and beta, it is Hurwitz. I don't need to do this for undirected graphs, but since we have directed, I checked it is Hurwitz. I choose C1 to be 1, 2, 3, 4, such that if you remember from the previous videos, once the command is 10, first agent should converge to 11, 12, 13, and 14 because of this one distance between each other. You can take this, you can play with KCIs, you can look at the guidelines I give in the previous videos on how they should be selected KCI, or what are the implications of them to be chosen, which agent converges to their where as compared to other agents. We discussed this in the previous video, but if you still have any comments, let me know. I will try to answer. So this is the states of each agent. They converge their formation, and velocity is as expected to go to zero once agents converge to a constant position. And this is shows, you can combine, you can take this video, take this code, make CL with time varying. If you would like to increase the speed of convergence, you can increase alpha and beta as well. You can play with those numbers. And as long as you play for directed case, make sure it is Hurwitz. Undirected case, you don't need to bother, thanks to this analysis. So as this being said, we end the video here. And if you have any questions, let me know. Thank you.